Hey, what's up, guys? Yeah. So recently I'm busy, so maybe the algebraic geometry video list will be a little bit delayed. I'm still keep updating. So in this video, let's talking about some terminology about the tensor product of OS module. Also, there will be no proof in this video, but just some terminology and then some fact that some fact that maybe the proof usually is tricky and cumbersome, so you can find it online or in the future. Then I will give you proof. So we already say the OX module, right? So we already say what is OX module, and so basically ring space and what is the OX the sheaf of module. Okay. So if we FGR to OX module. For our settings on some ring space, right? We have some list. So skin is a special example of ring space. So FGR to works module, and that we can define a FG or X. Okay, so the definition is very simple, right? So when you try to do a tensor product, right? So these are module, right? So you can do the tensor product of module. So if with the idea is that for each open set U, that I would, right? If I so I naively I can say that FU, right, and the OX U, right? So this is OS module and the G of U. Okay. So this is a simple definition. But the idea is that this is not a sheaf. Okay, so this is a little bit tricky. And so you can do the sheafification. Okay, so you just do the sheafification. Sheafification. Okay, so remember that given a pre-sheaf, you can do a sheafification. Okay. So this guy is a pre-sheaf. And the ones who do sheafification, then the results is defined to be so this is the OX module or sheaf of OX modules. This is called the tensor product of OX module. Okay, and recall that sheafification doesn't change the stocks, right? Those stocks. So I think in the previous one video that I proved that if you do a pre-sheaf, pre-sheaf stock X is isomorphic to the when you do the sheafification and X. Okay. So you can check that when you take the P and the OX, that there's some points that is the same as FP tensor G of P and the OXP. Okay, so yeah, so this is the definition of the sheaf of modules. Okay, and okay, so yeah, that's it. So this is the definition. And it has some lots of property like which is, yeah, I mean, we were talking about property. Okay, so now let's say given a definition of locally free sheaf, locally free. Okay, so when I say, and let's say when OX module F is called locally free. So imagine it's like a vector bundle, right? So basically it means that for every like for every X belongs to your space X, and there is an open neighborhood. So this is open neighborhood of X, such that when you restrict F, right, at some open set U, it's isomorphic to the OX, right, to some power, so some index I. So this is the tensor. Okay. Yeah. So U. Right. Yeah. Okay. As OS module. Right. Okay. So this is the same as, right? And if you know about vector bundle, right? When somebody say E could B is a vector bundle, basically means that for every V, for X belongs to B, there is an open neighborhood. There's a U such that the pi inverse U is isomorphic to U tensor with some Rn. Okay. Yeah. So imagine that there is some OX indices. Right. Okay. So let me let me just spend a little bit to describe what is OX indices mean. Oh, so it's not tensor. So it's a direct sum. Okay, so yeah, so this means that, so let me just sum. This is not a tensor. Sorry about this. This is direct sum. Direct sum. I'm stupid. Yeah. Right. So this is the direct sum. So this Rn is just R direct sum R right, as a vector space. Okay, so we can simply define this OXI to be the shiftification. Right, it's very simple. We take U, and it become like OXU, right? And then we take the direct sum, right? Because it's module, so I can take the direct sum. Then I do the shiftification. So the same trick as the tensor product. And I will get this OXI sheaf. Okay. Okay, so this is the definition of locally free sheaf. Okay, so it's basically locally it's like OX product. Okay, or OX direct sum. Okay, so if I is finite, then we call that F is finite ring. Okay, and okay, for every x that I is the set number. So these are fact that I will not give the proof, that I just list them as set number. So if for every x I is a set number, then we say F has rank n. Suppose this is n. Okay. And if n is 1, then usually this is the famous one called invertible sheaf. Okay. Okay. And there is a fact that we will prove. Very simple. Basically, if F is a locally free sheaf, then the F is a quasi-coherent. I think I have not yet spent time talking about quasi-coherent, but basically the quasi-coherent means that you can find index is I, index is J, locally and F to 0. Okay, for some open set U. And you can write down by definition, right? There's obviously that this is surjective map. Also obvious F is quasi-coherent. And if OX coherent, then any locally free sheaf and locally free OX module of finite ring is coherent. Okay, so now we can also define something, right? So basically, there's a canonical there's a canonical OX there's a canonical OX module homomorphism. Okay, what kind of it? It's basically you can define a dual, right? So if you start from L, which is, let's say you take L to be invertible, so you can sorry, not necessarily invertible, just some L. You can define L tensor F, so OX is defined to be home of OX module, so LOX, OX, tensor F, OX, and this is the same as homomorphism of OX, LF. Okay, you can try to write down the canonical one, but basically this is the same as this. If you do the vector space, that hopefully is simple, right? Because in a vector space, that dual you can just simply write down dual. Okay, so basically this shows that if L is invertible. By the way, this is the dual of, so L dual is defined to be home of OX, LOX. Okay, so if L is invertible, immediately show that L dual is invertible. Oh, invertible. Okay, and also one can show that if L is invertible, and then L tensor L dual, OX is isomorphic to OX. This is almost the same as a vector space proof, right? When you just write down, you just check it, you just check this on at the local at the stocks. Okay, and so the important fact also is that if L is invertible, and the L and another let's say L1 is invertible and the L2 is also invertible, then obviously that check by it's a vector space, right? If you have two-dimensional one vector space, their tensor will be still one-dimensional. But if you have two one-dimensional vector space, then their tensor still be one-dimensional. So L1 tensor L2 will also be invertible. Okay. So from previous one, we know that there is a dual as OX, and obviously that due to the module property, right? If you do the OX module, tensor OX module itself will be the same as L. Okay, so combine everything that we can define a idea called Picard group. Okay, so let me just write down. So isomorphism class, let's say isomorphism class of invertible OX module forms a group. Okay, so called Picard group, Picard X. Okay, Picard group. Okay, so right, so let me just write down. So what is the product? Right, so products defined to be the tensor products. Right, so tensor product. You can view it as a vector space if it's simple for you. So tensor product. And what is the identity? Identity is just the OX module or sheaf. And the inverse will be dual. So we have L, that you just L dual. Okay. Yeah. So the final fact that also is simple if you have the some rings homomorphism or some morphism between the ring space. If you start from some G which is locally free, if G is locally free on OY, then you can do the pullback, right? So if you do the pullback, or you pull back this, let's say this, right? You pull back this G, then one can show that the pullback is locally free. Okay. When simple, you can check by yourself. Okay, so now we have the idea of the product, tensor product. So I think these are basic terminology that you will need it. And in the next video that we can talk about coherent quasi-coherent sheet. See you guys next video.